Hi, and welcome back to the first video in the fourth lecture on Covidenomics. First, just a reminder of where we got to last time. We were considering the end games that the government could aim for. The first being eliminate the virus, the second being this beta approximately equal to 1 or a hard lockdown. Then there was the soft lockdown, which I've summarised here as managed beta. And then there was get to herd immunity threshold by allowing the virus to run. And last time we focused on this last end game and the actions required to get to that end game. And the argument last time was that this is probably incredible. In other words, if the government starts down that A4 path, letting the virus run, at some stage, as the bodies pile up, the government is politically going to be forced to change its mind. Knowing that is going to happen in the future, say around July, the government in March would be more sensible to say, let's choose a stronger action now, let's act earlier, as that'll be a better outcome for the entire economy and for the government itself. So now we want to start considering the three other branches of our decision tree that lead to these other three endgames, and look at what's going to happen as the government starts moving down one of these paths. But in order to decide which one of these paths the government would like to go down, the first thing we have to do is be a little bit more precise about what the payoffs are. In other words, each of these endgames is going to be associated with an economic cost and a human cost, and we need to be able to compare them. Now, the problem is it's a bit hard normally to compare, say, a 4% reduction in national income with the loss of, let's say, 5,000 lives. But we have to do that because otherwise we can't compare these outcomes because they're going to involve different economic numbers and they're going to involve different numbers in terms of the health cost, the loss of lives, the number of people who are sick. So we're going to need to turn economic cost and human life cost back to a common number so that we can say, well, is it better for us to bear the cost of eliminating the virus, or is that actually a lower payoff than if we try and have a hard lockdown? To do that, we're going to need to turn the health cost, the loss of life, into a dollar term. In other words, what we're going to be looking at in the next couple of videos is we're going to be putting a value on human life. This all might sound a bit like economics, putting a value on human life, but it's actually better than the alternatives. So think of the two obvious alternatives. One is saying you can't put a value on human life. That risks having human life ignored. And in fact, if you look up one of the references at the end of this set of videos, you'll see the story about the US Air Force and how back in the 1950s, they tried looking at different policies without putting a value on human life. Well, that means that machinery and equipment gets valued and dead pilots don't get valued. That makes no sense. So saying, well, we can't put a value on human life, so let's ignore it, is a pretty bad outcome. The alternative, of course, is to say human life is valueless. It's infinite value. You can't put a number on it. But we know that that is simply not consistent with our individual behaviour. Whenever you cross the road, whenever you get in a car and go for a drive, whenever you go out for a jog in the park or go for a bike ride, you're taking risks, and you would not be willing to spend all your wealth to eliminate those risks. You're willing to take small risks with your own life, even when it may be possible to pay to remove those risks or to take other actions. Just stay at home, stay in bed, to remove those risks. So we know individual behaviour is not consistent with saying, even my life has an infinite value. I will take risks. Sort of life would be pretty boring if we really behaved like our lives were infinitely valuable and took no risk with them. The second is, even if you're not convinced by that argument, government policy clearly does not put an infinite value on human life. Think about car safety policy. If we really put an infinite value on human life, we would not let any cars on the road, because cars are nasty, dangerous things. They hit people. They're involved in accidents. You certainly wouldn't let people drive cars. You might say, look, we'll put more money into researching automatic driving cars, but until then, you guys stay off the road. Because the risks are too high, you might lose one of these infinitely valuable lives. That doesn't happen, and quite frankly, any government that suggested it would be out of power pretty quickly. So we don't put an infinite value on our own lives. Government doesn't put policy in place to put an infinite value in our own lives. But we certainly want our lives to be considered by policy. We don't want them to be valued at zero implicitly by being ignored in policy. So we better put a value on human life. Otherwise, we're going to end up in a really nasty policy space. Just before we leave this slide, however, one slight note on terminology. Some of you, if you've looked through some of the literature, will notice they don't talk about hard and soft lockdown. What we've actually got here, when I talk about hard lockdown, that's sometimes suggested to be suppression of the virus. And when I'm talking about a soft lockdown, this managed beta strategy, that's sometimes referred to as a mitigation strategy in the literature. That being said, the literature's not really that clear on what mitigation is and what suppression is. So I'm going to keep using the terms hard and soft lockdown because I've defined them in terms of this reproduction number beta. So it's a bit better defined. So the three things we're going to be looking at in this next series of videos are: how do we value a human life? How do we value a year of life? And then how do we adjust our value for quality of life? The first one that we're going to look at is the way to value a life in terms of the present value of future earnings. So here's the example we're going to start with. Ashish is age 20. He will work for the next 40 years, and to make life nice and simple, he's going to earn $40,000 per year in each of those years. He's then going to retire when he's 60 years of age, so we'll allow him to retire for 20 years, and then at the age of 80 he's going to die. So, given this information, how do we value his life in terms of future earnings? There's two things that we're going to need to be able to solve this problem. The first is we're going to need a social discount rate. In other words, how do we translate, say, Ashish's income in 10 years' time back to current dollars? How do we translate his income in 15 years' time back to current dollars, and so on? That's the social discount rate, and we talked about that very briefly earlier on when looking at exponential growth. And second, we're going to need a bit of mathematics to work out how we add up all the numbers to get to his present value of lifetime earnings. Let's start with the maths first, because believe it or not, that's the easy bit. So here's a bit of maths. We need to work out the net present value of Ashish's future earnings. We're going to assume that Ashish gets paid at the start of each year, just makes it a tiny bit simpler. You can easily work it out if you just delay it for a year. But he gets paid $20,000 today. Then in a year's time, he's going to be paid another $20,000. But to turn that back to today's income, we need to divide that by 1 plus R, where R is the social discount rate. Then he's going to be paid $20 or $20,000 in 2 years' time. So again, we have to take that $20,000 and bring it back to present value, which is dividing by 1 plus R squared, and so on up to 39 years in the future when he's paid his last lot of $20,000, and we have to bring that back to present value by dividing by 1 plus R to the power of 39. If you're saying, where does all this maths come from? Go back and review the first sets of videos from this series, because where we talk about exponential growth, that's where we explain where this comes from. This is just exponential growth working in reverse. To solve this bit of maths, we're going to use sort of quite a neat trick. What I've got here is called an infinite geometric series. So a plus ab plus ab squared plus ab cubed plus ab to the fourth, and so on. That will have a finite value if b is less than 1. We can actually add this up and work out what it is in the limit as our exponential goes to infinity. And there's a nice little formula for that. I can never remember the formula, but it's easy enough to work out, and I'll show you how. To do this simple trick, let's just write down our infinite geometric series again, but multiplied by the term b. So xb on the left-hand side equals, well, a times b, ab squared, ab cubed, and so on. Now I've shifted that right-hand side across a bit because we can now take the second equation off the first equation. Note that if we do this, it's really, really simple, because on the right-hand side here, we have a minus 0 is a, ab minus ab is 0, ab squared minus ab squared is 0, ab cubed minus ab cubed, and so on, up to infinity. So all of the other terms on this right-hand side disappear except for the term a. So on the left-hand side we have x minus xb from here, right-hand side we have a, and then it's very simple to solve for x, the value of our infinite geometric series. And that is, to solve our infinite geometric series, we know that x is simply equal to a divided by 1 minus b. Only one problem here: this is a finite geometric series. It stops after 40 terms. How do we work out that? Well, another simple trick. Let's just define another infinite geometric series. We're going to call it y, and the only difference is its starting term is going to be a times b to the power of n. And then it's going to have the same multiple every time you're just multiplying it by b. So we know what that is. It's going to just fit into our above formula, except a will be replaced by the new first term, a times b to the n, divided by 1 minus b. And if we now take y away from x, we're actually solving for a finite geometric series that has n terms. And that's just equal to the value of x, a over 1 minus b, minus the value of y, a times b to the n, over 1 minus b. And we can just simplify that into this formula here, which a lot of you will recognise from high school. It's a formula for a finite geometric series, and you were probably given it in high school and it wasn't explained where it came from. So now we can go back to our problem with Ashish. Notice that our a is going to be 20. Our b's a bit of a pain. The b is 1 over 1 plus r. So we're going to have to shove 1 over 1 plus r in a couple of spots. The n here is going to be 40 because we've got 40 periods. And this is our formula to work out what Ashish's life is worth in terms of the present value of future earnings. So here's what our formula is when we're using a 4% social discount factor. And that gives us a net present value of Ashish's future earnings of $411,684 approximately. And we can use that under this approach as the value of Ashish's life at the age of 20. Couple of things that might strike you as a bit worrying here. The first thing is that Ashish's value of life falls over his lifetime. He has fewer future earnings to be discounted back, and goes to 0 when he retires. So at the age of, say, 65, according to this approach, Ashish's life is worth nothing, even though he has 15 more years of life to go. Second, let's suppose that Ashish still has 5 years worth of schooling. So he's aged 15, and he's going to finish his 5 years worth of schooling before he starts earning his $20,000 a year. Well, according to this approach, his life would now be worth less at the age of 15, because of course we're not dealing with a finite geometric series starting at 20. We'd now be discounting that 20 back for the 5 years of education he's got, and doing that to the entire stream of income. So if you're younger in life and haven't yet started earning, according to this approach, your life is worth less than if you had started earning. And that seems wrong-headed, that you're somehow discounting a person's life back when they've got more opportunities. Third, there's pretty clearly some significant equity issues with this approach. So if you have fewer opportunities and you can only earn less money during your lifetime, according to this, your life is worth less than otherwise. Or if you're part of a group in society that systematically gets paid less, your life is worth less. Or if you live in a country where salaries are lower, according to this approach, your life is worth less than another person's. And that seems a bit awful. And finally, we could take this even further. We could say, no, we've overvalued Ashish's life. Surely his value to society is his output, as captured by his future earnings, less his input costs, captured by his consumption. So shouldn't we be valuing his life as his net present value of future earnings, less his net present value of future consumption? Sort of a bit like a machine. You work out its value by looking at its output, less what it costs to run the machine. There's some ethical problems there. Essentially, you're saying that the value of a human life would be measured by how much surplus it leaves for the kids. My kids might like that, but it doesn't sound too good to me. Just to illustrate some of these effects, let's look at some numbers from the United States in 1964, and they're from this article down here, which was published, I think, in 1967. And they sort of capture the type of things that we're talking about. Firstly, let's look at males and let's look at the all category. And you'll notice that as people get older in their working lives, the value of their life gets smaller and smaller because, of course, their future stream of earnings is getting smaller and smaller. And in fact, someone over 85 years of age in this approach isn't worth very much at all. Secondly, notice that, again, younger, when you've got education ahead of you and your future earnings are further into the future, your value of life is lower, and it gets higher as you approach those useful earning years of your life. So, a person under 1 is only worth about $59,000. That same average American, if they were aged between 15 and 19, would be worth about $114,500. Thirdly, notice that you get those issues of equity here. So two clear groups, whites and non-whites within the US. There is clearly discrimination against non-whites in the US, as there are in a number of other Western societies. They get paid less, and you see this in the numbers. So let's take our 20-year-old. If Ashish was a white male in 1964 in the US, his life would be worth $134,000 according to future income. If he was non-white, then he would be worth less than $75,000 on that same basis. And that just seems, well, quite frankly, straight out racist. Similarly, we see built-in differences between males and females on this approach. Many women back in the 1960s did not work. There was clearly sexism and discrimination in the labour market, as there still is in many countries today, against women. The problem of measuring lifetime wages for women was made more difficult because many women worked in the household and they weren't explicitly paid. This study was that I'm using here was quite forward-thinking for its time, in that it actually valued household work of women, but that was not particularly usual in the studies around this period. But even so, you see the clear issues here. A white male, 20 to 24, life is valued at $134,000. A white female of about the same age, you're looking at $73,419. And again, you see that disparity between white and non-white. This second table shows how the value of life depends on your educational opportunities, because they will feed directly into your lifetime earnings. So here, again, let's take 20 to 24 as the relevant age cohort. Here we've got white, and we'll look at males. A white male with only 8 years worth of school at that age, their life is worth about $112,000. If they had 12 more years of schooling, $150,000. If they had 16 or more years of schooling, or that was expected of them in their life, their value of life would be $209,000 if we're valuing their life on the basis of future earnings. One final thing to note here is these are all done at a 4% social discount rate. That's not obviously the correct social discount rate. Some people would argue that it should be lower than that, or even zero. Some people would argue it should be higher than that. And often in Australian policy, around 7% is used for the social discount rate when we're considering any policy involving government funds. So if the social discount rate was higher than 7%, so we're discounting back by more, future dollars are worth less in today's terms, that would lower all of these values of life. If we were using a lower social discount rate, then we would be pushing the value of all of these lives up. So where does that get us? Well, we can value a person's life based on the net present value of future earnings. But hopefully I've convinced you in this video that that's probably not the best way of doing it. And that was recognised pretty much in the 1960s. And Thomas Schelling is often credited as being one of the first people to say this is just a wrong-headed concept. What we need to do is think about the value that a person shows they put on their life through their actions. Thomas Schelling, by the way, one of the giants of economics, went on to win the Nobel Prize and one of the founding fathers of game theory. You'll come across a bit of his stuff in this course and in most other economics courses you do. But that's it for now. Next video we're going to turn to this idea of a value of a statistical life based on an individual's choices.